And I'm recording now, and let me get this up so that you can. Let's see if this would happen. There we go. That's what I was trying to get to. All right. Thank you all for being here. I hope you all signed in. If you haven't, please do so. Excuse me. I'm Kelly Raymond. I'm the program coordinator for the Interfaces program, and I'm so glad that you're all here today, and I hope you're enjoying the meal. We're very fortunate today to have Dr. Matthias on Herrath.
Very good.
I practice with us today, and for those of you who may be new to meeting Dr. von Herrath, I want to tell you a little bit about him. He is a professor and he's an MD, and he's highly respected and an accomplished physician scientist in the field of immunology and drug development for type 1 diabetes in the academic medical research as well as pharmaceutical sector. He's the scientific director of the Diabetes Research Institute and Stacy Joy Goodman Chair at the University of Miami School of Medicine, where he's leading the DRI mission to conduct and accelerate research to delay, prevent, and ultimately find a cure for type 1 diabetes. He is also the vice president and senior medical officer of Novo Nordisk, a global healthcare company that specializes in diabetes care and treatment. In this role, he oversees the clinical development of Novo Nordisk's pipeline of products and therapies, ensuring that they are safe, effective, and meet the needs of patients worldwide. Prior to joining Novo Nordisk, Dr. von Herrath was a professor of immunology and medicine at the La Jolla Institute for Allergy and Immunology here in La Jolla. He also served as director of the Center for Type 1 Diabetes at the Institute and held positions at the Scripps Research Institute. So we're so happy to have him today, and please join me in welcoming Dr. Matthias von Herrath. Thank you.
Thank you for the nice introduction. I'm very happy to be here. The agenda is we will talk about diabetes and treatment options a bit in the beginning, and then we will talk about things I'm passionate about in general. And as I see myself getting older, I become more passionate about them, which is the careers in biomedical sciences, the robustness of science and reproducibility. And I try to do this all in a way that we have still some time to discuss things at the end, right? Do we have a hard stop at 1 o'clock, or how does it work? Okay, so we can see how it goes. You should also feel free to interrupt me any point of time, and you can ask me any questions in between as they come up. That should be fine, and I can adjust the talk then according to the time. That's really not a problem. I'm going to start with my roles are, let's say, unusual for the biomedical field, and I actually went in 2012 to join the pharma industry because I was very interested in translating things for patients, some of which we had worked on before. And I was also very interested in having a framework where we could do very solid reproducible science. And it was these reasons that made me transition. We then made, because I retained academic activities over that time, and it might interest some of you how that gets done. We made a very good conflict of interest arrangement, as is obviously as needed in situations like this, in the sense that when you work for a pharma company, you can, of course, not consult for other pharma companies all over the place. And they can also not dual gain in the sense that you cannot foster things in academic science that then also profit the pharma company and vice versa. So we appointed ombuds committees for all of these situations so that you cannot play both sides. But altogether, it's actually pretty easy and clean. You don't play both sides. You stay true to your mission, and you don't mix these things up. And we have done it for a long time, and it has worked pretty well. And more recently, when I took on the scientific direction of the DRI, I closed all my academic lab activities, mostly because, as probably many of you know, certainly Vera knows that writing grants and maintaining these type of things can be rather time consuming and complicated. And I felt that would of course be too much. So that's my situation. We can discuss that if you have questions at any point of time during and after the talk. Type 1 diabetes, and I don't know how much you know about this disease, but it's an interesting disease. It falls in the sector of what people call organ-specific. They call it autoimmune diseases. We probably should better call them diseases with strong autoimmune or self-reactive immune participation. So it's a disease where an organ is affected, in this case, the islets and the pancreas. These are these little red dots you can see here. They make insulin and glucagon and some other hormones that are really absolutely vital for our survival. So it's an important sequestered site. There are many other such autoimmune diseases. Alopecia, where you selectively lose your hair in certain areas, is one of them. And there the process is in the hair follicles. Arthritis is an organ-specific autoimmune disease to the most extent, but it has some systemic aspects and so forth. And it fascinated me from the beginning how this could happen, that the immune system that we have to defend us against viruses and bacteria, fungi, why would this start attacking your own body pieces? That I always found very fascinating. And summing some concept up in the beginning, the thinking was over many decades that this is a problem where the immune system is not rightly educated. And you have cells that are not controlled, that see your own organs. I tend to think from the pathology that we have studied now for 15 years in human organ donors, that this works a bit differently. You have this miseducation of the immune system, but you also have the organ itself becoming visible to the immune system. And I will tell you some of the mechanisms we see that underlie this, because I believe that this happens probably in several of the autoimmune diseases, also multiple sclerosis. One indicator we have here, when you look at the pancreas, it's lobular. And you see some red areas where the islets that have insulin that usually stay in green are already gone, but the islets are still there. The red is the glucagon they also make. And then you have some other lobes at the bottom, you see it, where we still have intact islets. So it's a lobular disease, which would not be really inferable or explainable by random immune events. There has to be something local that tells one lobe it's ready for destruction versus other lobes. So it progresses lobular and affecting certain areas. And it's also in its prodromal phase that the islets in a way burn down randomly, lobular, but only few of them. So you can be pre-diabetic for a long, long time and you lose islets. You make then antibodies to the islets, but you do not fall off the cliff. The biggest challenge for these diseases is, the way I see it, and maybe one of you can write a cool model about this, is to predict a complex feedback loop system. It's similar, I make the analogy to the climate. And when this system reaches a tipping point, this is very, very difficult for patients because they come, they have antibodies, they go like, well, what now? We're going to have diabetes next year or in 9 years. And you tell them, well, you have 2 antibodies. Maybe you have diabetes with about a 9% likelihood sometime in the next 11 years. That's, of course, not very useful from a patient perspective. And it makes it more difficult to weigh risks for prevention or therapy, because it's different whether you get something in 30 years or whether you get something 1 year from now. And that's something nobody has managed to really predict, not based on biomarkers, not based on understanding the systems and the feedback loops. And I would love in my lifetime to see such a model. That would probably not only be cool for type 1 diabetes, but many other areas where if you can predict tipping points. I think that's how the system works. It is indeed such that the islets are lost when it reaches a tipping point. You go from not being diabetic to diabetic within about a year's time frame. So it happens pretty fast, but you can be pre-diabetic for 3 decades. And then you reach this tipping point, maybe a trigger like a virus infection that pushes everything over the brink, and then poof, the system collapses. We are lucky, of course, in a sense, we have insulin. Otherwise, this used to be a death sentence. before the discovery of insulin. And insulin delivery and devices are becoming better. So that sets a therapeutic framework in the sense that you cannot take the immune system away from patients if you can survive on a glucose sensor or an insulin pump reasonably well. And then there's, of course, socioeconomic differences, other differences. But if the country is well-to-do, you can have a normal life expectancy. And there's many socioeconomic differences. If the country is not well-to-do, then you can't. I mean, that's a different problem. That's what we think, what happens. It's very curious. We don't know the triggers at all. There's some genetics, but what distance and area for destruction is not clear. I tend to think that these organ-specific diseases are maybe driven by a dysfunction in innervation. And there are some indicators that this might be so. When you look at vitiligo, where you lose pigment in your skin, there's a symmetric form of vitiligo. And unless you have another explanation, I wouldn't see how you could explain to a lymphocyte that precisely on the left-hand side of your face, precisely on the right-hand side of your face, they have to attack the same area of your face. There has to be something that leads there that makes these areas special in the symmetric forms of vitiligo, where we can see it well. And I think it's innervation. Viruses, we looked for 30 years. For sure, we can conclude it's not one single virus. They're general infections because they make you insulin resistant and they can mess with your organs, and COVID falls in the same situation. They can push you over the brink. It's never a great situation if you're severely ill for 2 weeks. Doesn't make you stronger for evident reason, and can mess with all kinds of systems in your body. And so viruses could push at least patients over the brink, but they are only in very rare cases the primary cause. Then autoantibodies are produced. They didn't cause disease as far as we understand it, but a very good predictor of disease risk, but not individually, but generally. You can say patients with 2 autoantibodies have lab increased risk for diabetes, but you cannot tell, as we discussed, where the individual tipping points are, which is a gap. And then things occur actually before the immune system arrives. One is that MHC class 1 immune recognition molecule goes up on the islets. And with that recognition event, then these islets, as we think, are destined for destruction and they become visible to the immune system. It's almost like removing a Harry Potter cloak from a highly protected organ. We think it's like this in the brain, and we think it's like this in hair follicles. Otherwise, the immune system doesn't take business to take attack on your organs. Actually, if you scratch your finger, the default is things heal. You don't get a skin autoimmune disease from scratching your finger. The immune system goes there, checks out, is there germs in there? If there's no germs, that drives the wound. The default is to close the thing, and then the shop is closed. It's not like you develop autoactivity to your skin. So that's how that works. Once patients are sensitized, it's a problem, because you make memory cells that then recognize in type 1 diabetes pieces of insulin. Once you have them there, they sit there like any memory cell, and they, from all we know, behave like memory cells. In this case, they sit also in the exocrine pancreas. They wait to see their antigen. And this is usually good for COVID. We have, for example, learned the more memory cells you have, the better you're off not to become severely ill. That's the general notion. So memory cells are good. Memory cells are good for flu. Some of them remain in the lung if you had an infection, and their role is to protect yourself. But it's very difficult to remove them. They also control herpes viruses endogenously. So removing all memory cells from a human being means that all kinds of virus infections will flare up. So it's not an equipoise. You can choose to treat this disease. And it's probably the biggest problem. And they're good, these cells. It's like almost like an allergy. You can be, like in my case, I'm allergic to grass pollen in Germany. You can count on it. If I go back there, it takes me 1 day, I have the allergy. Here I don't have the allergy, but the cells are sitting there. They're just waiting to see this antigen with a very high specificity. So that's how it works. When you see these islets, it's interesting. There's class 1 on an islet. That's how they look. Green are the beta cells that make insulin. It's like the islet switches on a light bulb. Usually they're just black. And only after that, we think the immune system becomes interested in these islets. So that's how that works. There's many things we don't know. I already alluded to that. Is it innervation that causes this organ unveiling and dysfunction? Is maybe a good hypothesis. Is this virus persistence? Maybe. And the exocrine pancreas could have a role in this. In terms of those who like to play with devices and engineering something, especially at the DRI, which I find most fascinating, there's now companies who are developing what they call these electroceuticals. And these are devices that you can put on certain nerves in the human body, and then they change how the nerves signal to immune organs. There's one company called Galvani, their CEO. I like the concept, so I rang him up. Their CEO is Chris Pham. He was several years ago one of Time's 100 most creative people. And they have built these electroceuticals to suppress inflammation. So you could envision at some point that we control inflammation through devices where you say, oh, Matt, your knee is hurting. Let me put this Starship Enterprise device on your leg, and the inflammation will go down. You're going to be fine, and you don't have to take systemic immune suppression. So there's many things when we discover these interfaces that can still be solved, and maybe in ways we can't even fathom at this point how that could go. There's questions who is in the driver's seat, whether different patients have different immune responses. We don't know that for a fact. It seems very interesting, at least in mice. Once you have a cell in the driver's seat, it always stays in the driver's seat. And they don't like to give up the driver's seat. Sometimes like academic hierarchies could work. So it seems like it also has some truth in driving the islet attacks. And we don't know why that would be happening. And we know too little about the gut immune interface to really fully explore it. And it's not easy. There's some very good groups also here at UCSD who are working on that, but you have over 400,000 gut bacteria. So sorting through this and finding whether there's now 1 or 2 or 3 that colonize that might drive diabetes is a difficult exercise. But I've been fascinated. When I started my postdoc at Scripps in 1991, because of the genetic similarities between mice and humans that had just been discovered, there were some professors who were visiting that told me, Matt, there's no use studying this. We're going to be done with this in 1 year. And I was, of course, I had just started, so it didn't make me too happy. I thought, great, I have a project that's going to end really soon. That's going to not go so well for me. And then I talked to my mentor, was Michael Oldstone, and he said, no, Matt, we're staying on track. This is not going to be so easy. And now we are still at it, right? So we underestimated how complicated the origin of self-reactivity is. But it affects all of us in many ways, not only because of type 1, but in the general magnitude of all the different autoimmune diseases, if we are unlucky, each of us can get. And it's because of that quite substantial problem. And our arsenal of treating the diseases, as I mentioned before, it's not big enough. We have systemic immune suppression, but systemic immune suppression has side effects. And systemic immune suppression can cause a preponderance of certain cancers, and also, as you would imagine, heightens your risk for infection. So it's a trade-off. It depends, of course, how much, which immunosuppressant, but a full immunosuppression, if you get an organ transplant, is not really a ride in the park. It's a difficult situation. If it's life-saving, of course, it's very good, but it's not an easy predicament from a patient perspective. So we have to keep that in mind. I'm going to say a few things about interventions, and then we go in the career part. So you can intervene. We are most interested in intervening early and preventing the diabetes altogether. In that phase where the system is still stable, we think it's actually relapsing, remitting, because there are times where no immune cells are in the islets. Before this cataclysmic tipping point occurs, where patients lose most of their beta cell function, and it's kind of, so to speak, downhill from then in terms of preserving the beta cells. But at this point here, there's not so many beta cells still left, and then you will have to put them back. There's good approaches from stem cells that people are doing this, most notably the company Vertex, but you also have to immunoprotect stem cell-derived beta cells. They are an allogenic transplanted organ by and large. So you have to keep the alloreactivity away, and as I mentioned before, the memory cells will get extremely happy seeing their antigens again and will become woken up. Yes?
I realize this is a cartoon, but on that last week before that
Yes, it was, but there's still a little bit of theory and hypothesis about this. When we looked at the insulin surface area in the pre-diabetic phase, then what is happening is it doesn't go down. It's not linear. It seems the system is fighting back and trying to stabilize itself, and it oscillates a bit. And then all of a sudden, when there's too many disturbances, it reaches this tipping point and re-equilibrates, right? And that seems to be happening in type 1 diabetes, and the immune participation in this time is most profound. So it plays a role that probably that you reach a critical mass of immune reactivity to the islets, then that pushes the system over the brink. I give you some ideas how we're trying to reset the system. We really would like to see combination therapies in immunology. We have been working on this for decades, that you induce the system with a reset, but short time, and then put a maintenance therapy to log in the benefit so that patients don't have to be on permanent immunosuppression. I don't think that we can get true tolerance without maintaining it. The immune system in all of us kind of works in a way that if it sees something all the time, it becomes more easily tolerant. If something comes suddenly, like in a vaccine, it will make an immune response. So this balance, I think we have to be quite mindful of. I think as human beings, at any rate, we are engineered like this. We tend to be more worried if there's a tiger on the terrace than if there's a more insidious thing that could damage us, that very slowly and progressively, let's say in our environment or elsewhere, increases. And I think to make things tolerant, we will have a maintenance therapy that is tolerable altogether. We have been working on some drug classes. They're interesting, that affect the interface of the beta cell with the immune system. The first indication had come from a paper, and these are these GLP-1 drugs. They're right now used quite widely for weight loss, but at lower dosages, as we think, and also for type 1 diabetes, as one can hope, but it's not allowed at this point, and it hasn't been tested properly. We think they could change the beta cell immune interface. And we have built some organoid models where we wanted to see whether we could protect mini islet organoids. So we put these organoids, we worked with an engineering company in Switzerland called Ensphero, and we put them under immune attack. So they are mini islets reassembled, human, and we put lymphocytes on them or clones. And then we see whether we can maintain insulin secretion. And this is in a 2-week time frame. And I show you just the readout because I think organoids, especially from human organs, can be very useful because you can isolate problems and you can do it faster, easier, more ethically, and in a more rapid way. So the insulin secretion, it goes down when immune system encounters these islets. But if you add these GLP-1s, at least for the time frame here, you can maintain or improve this in a dose-dependent fashion. Whether that's therapeutically useful, one has to see. This one here, you can see how this organoid looks. I don't think the movies are going to run. But you can see the organoids get chewed up by the red lymphocytes, and interfering with this process is actually quite a feat because it's an overkill situation in vitro. The other thing we have done, we have run a big trial with a combination therapy where we use an immune modulator and one of these GLP-1s, and we try to preserve beta cell function after onset. You measure a piece that comes out of the production of insulin, it's called C-peptide, to understand whether you have preserved significantly the beta cell function. And in this case, we observed for 1 year, and then we washed out the drugs. So patients were on the drugs, on the combi for 1 year. And it was the first adult large phase 2b trial ever run with about 311 patients, and we reached endpoint. So we think that the combination of things that improve the beta cell health and at the same time tackle the immune system is useful. And now our task will be to put this into induction maintenance therapy, so to speak, so that we can use the immune modulators like we used the anti-IL-21 for a year. Ideally, you would use it down the road as an induction therapy, or not longer than a year at least. So that's the aspiration. So we preserved here beta cells. That was a pre-specified endpoint. We reduced insulin dose, also a pre-specified endpoint, and we had good trends on glycemic control that is measured by HbA1c, and we had good trends on avoiding hypoglycemias where the patients experience low blood sugar events. So that's what we have done trial-wise and what we would like to build on. Overall, I think what we would like to do is we would like to build parallels between what we can do to prevent diabetes and what we can do when you put islets back into patients. I think the therapeutic paradigms are going to be the same. You can ethically not immunosuppress the patients, if in general, most of them, for a long period of time. So we want to get away from that. And we want to have maintenance therapies that could be useful in prevention, as well as when you put islets back into patients. We did the shark attack cage because often the islets are in bioengineered environments in a capsule. And that has been a struggle. We could talk about this for a long time. They need to have enough oxygen. They can't become fibrotic. Nutrients need to go out, they go in. Insulin needs to come out. But at the same time, the immune system should not see the islets in the cage, although it will be quite interested in them. And you want to build this capsule so you can avoid long-term immunosuppression. So in a nutshell, that's where the diabetes field is and where we are progressing. I made it short because I want to have some time to talk about the career aspects, but we can take a few questions about the diabetes part if there are open questions or something you might want to hear about. Otherwise, we talk about careers and reproducibility. Good, I go on. Okay. So these are the things I'm quite passionate about. I would kind of like to see our scientific enterprise undergo a revision, and it certainly concerns the medical and biological sciences. I would like to find ways that more robust studies are being done. And certainly we would like to see maybe more varied, not only better, but varied career path and less bottlenecks, so that everybody who goes into these fields has more choices. The robustness is a problem. When we look at academically published papers in industry, we see, and the Novo Nordisk experience is similar to what Amgen and others have experienced. It's somewhere between 60 to 80% of published work will not, it's not like it's fake, but it will not hold up in a robustness test, right? And you can look at this two ways. You can say, well, maybe these are just pilot studies that are published. Okay, fine. But then I should say, maybe I studied some mice here and I observed something that might maybe be useful for humans, more likely than not. But here's the stuff that I did, right? But that's not how we write our papers. And I'm as guilty as charged with that too, right? Because the whole system is inflated. It will more read, here comes the next cure for type 1 diabetes, and look at all these mice that have been cured from the disease. So there has to be some form of an atonement. Not only when you study animal models, but in general also the conclusions from human trials, from biomarkers and so forth. And we have to be aware of that. That's why we called it robustness. And I think it's important because it's important for the way science is viewed in the public eye. And it's also important for having open debates, because if I do something that's not so robust, and then you do something that's not so robust, well, if we both know it, we should have a conversation. It should not be an inflammatory conversation, because you might say, well, we don't know. And I say, well, we don't know. And it's a time to get together, right? And that actually attracted me a lot in the environment in pharma and also at the Diabetes Research Institute in Miami. This honest and clear, often transdisciplinary conversation one has to have in science, because it is hard, it is difficult. And for diseases like type 1, it is very difficult to do things. I talk first about the robustness. We had a paper in Cell Metabolism a while ago where we had, and it speaks to the robustness issue, where we had 3 cases, initially 4, but then 3 because of there was some, let's say, political interference, because as you can imagine, nobody was happy to have these cases debated, because careers and promotions depend on papers. You can argue rightly or non-rightly so, but this is an issue. So if you publish that something is not robust, you don't make friends. And this was the same situation here. And we said, well, we're a bunch of older guys. So if we're not going to do it, who else is going to do it? And we should stand up for this if this stuff didn't hold up. And it's not uncommon. You see it on the right-hand side. And for example, the NIDDK, because they're interested in interventions that will hold up, they try to reproduce, I think, 3 or 4 things with a CRO, with monies from an NIDDK, to make sure that interventions would work. And their readout, what in this case, was that 4 out of 4 didn't work, right? So for translation, for pharmacological translation in a pharma company, this is very important, because otherwise you organize a trial and then the whole thing fails. And you want to various reasons, most of all, so you don't expose the patients in vain, but then of course also for financial and drug development reasons, you don't want to shoot these blanks with the highest likelihood. And so that's the situation we are operating in, and it's tricky. What affects robustness? We have issues. You can go down the list. We have too much pressure to publish. And to be fair, of course, all of us should be productive. We also should publish everything we do, probably actually everything, most certainly also negative data. But we should not have our whole career hinged on a certain paper that then has to have positive data. That's not natural to the system, and it's also only one aspect. And I know what it was born from. Germany had a very hierarchical, stable system, and we used to have professors who would not publish one single paper over 3 decades. And you could say, well, if they teach, that's maybe okay, but maybe if they have a research program, they should let somebody know what they have done, because all of us would want to know, right? So we should publish, but it is only one of many factors that should determine where our career is going to go and how things are rated, especially since often many of us don't have control over it, certainly not of the outcome of an experiment, and certainly also not whether a journal might be interested in it. There might be, because of this pressure, some selective reporting for cost reasons. So the pressure to publish and then cost reasons are probably the biggest constrainers. You end up with low statistical power. We're going to come back to that. You end up with low degrees of replication, and these things are not so good. And experimental design should not be underestimated. And the recent suggestion by a good friend of mine, Jay Schuyler, he said, maybe we should do this the other way around. We first should discuss and design a good experiment, and you should register these experiments with a journal, let's say peer reviewed. Once we all agree that this is a cool thing to do, it should actually get published in this journal, because we already agreed it was the right thing to do. So then after that, if nothing goes wrong and the thing worked and nothing broke down, the data are the data. If they're negative, they should go in the journal as much as if they're positive, because if it was a well-designed experiment, that's then the answer to your primary premise and hypothesis. So maybe we can turn some of this around with this type of situation. And there's other factors that might play a lesser role, outright fraud and these type of things. They always reach the public, of course, and in a high profile manner. And you can imagine that a system with too much pressure will also result in fraud. I don't think, though, that's often the intent. Something we should keep in mind is that a robust design will actually be quite helpful. A friend of mine, Andre Liebinger, who he made this slide, he is a statistician for Johnson & Johnson here in San Diego. And we met on the soccer field actually during COVID, because it was the only place where our kids could run around. There was lots of fresh air and we're not going to get the COVID. So we had a lot of time to talk to each other. He used to call it the widow's curse. So if you have low powered studies, the certainty goes down, but then the possible bias you have afterwards becomes higher. And that's probably for financial constraint reasons a big issue. And then if you go into what actually happens to your experiment is the following. When you have many small studies, like on the left-hand side, and they're normal distributed, they will wobble around a little bit. Some are on the right, some on the left, some in the middle, sort of what we expect. But if we only publish the positive ones, we're going to end up with a new perception of a scientific truth, right? And all of a sudden we stand there and alternate truths are going to become real or not. But definitely we cannot make a decision on what the outcome has been of these experiments. And that creation of a new false reality, because the negative stuff is harder to publish and get out, this is really not good. This is a big problem in the biological sciences for sure. I think in some engineering areas it's better, because if you propose, at least that's what friends tell me, I'm not an engineer, if you propose something completely that's out of whack, the correction will be faster, because a colleague will find it and say, well, look at what you proposed here, that's never going to occur. And you have your white paper, and then you have 20 other white papers. Say that's not going to happen. But biological systems and things you try in humans, when you talk about the interface, they are harder to reproduce. They cost a lot of money to reproduce. And so whatever is out there for then stands. And if the negative part is not out there, you can't find it. And then you have to go through a system and talk to a lot of buddies and colleagues and find out whether this was already done before. But it gets complicated because it's just not there. So this is a problem altogether. We had this, I have some examples for diabetes, how that works. We use these animal models. And animal models, they are noisy. You look at here the diabetes incidence in a large NOD mouse type 1 colony. And this was in Seattle at Novo Nordisk. We put this in that paper I just mentioned. And you can now ask, if you try to prevent this diabetes, how big should the effect size actually be? And as long, we just concluded, as long as we are in this blue zone, we're not going to take any of this forward. We have a risk that we miss some things that might be valuable because they're not worked out properly, have a small effect size, but these are too shaky legs to stand on. And we were trying to induce what you would call, it's often done in allergy, you induce antigenic tolerance, meaning if you eat a lot of peanuts, then your peanut allergy might be less severe down the road, this type of thing, right? So we wanted to then desensitize towards insulin, because you could say if you do this only for insulin, the rest of the immune system stays intact. All these studies that have been published, not to belabor the single ones, it's not they were wrong, but all of this was too wobbly or not robust enough. The effect size was too small, and it was, in our eyes, not translatable. Now, we can have many debates about this, but that's how, in this case, the antigenic tolerance field in type 1 diabetes presented itself to us. And to make matters better or worse, whatever way you want to look at it, they also contain some of our very own studies. So we're not taking, I'm not preaching here saying, oh, well, we had done this all great. No, you have small resources, you realize you end up with papers. In our case, it was oral insulin to induce tolerance. You end up with things that are not robust enough for translation, and it's an issue. It's at least something we should think about. And the first paper, for example, on oral insulin, the effect size published was this, but the usual colony incidence is here. So it was maybe a colony that really didn't have too much diabetes incidence, and it's the reason we haven't been able to bring, as attractive as this concept still appeals to me, that you swallow oral insulin, hormonally inactive, you become tolerant to the oral insulin, and then you don't develop diabetes. It sounds really good, right? But we can't make it go for the clinic. That's where it hangs. It actually, to be fully, don't want to be misunderstood. Nobody committed fraud. Nobody forged data. None of this type of stuff. It's just not robust enough systems. And it means still maybe 20 years from now, we can work it out. But right now, it's not worked out. And what comes out of all these considerations is that would we have done it right in the first place if we would have given studies more power? Would we have published all the negative studies? We could have been done with this probably much faster than several decades. And that's where it really matters, because time, when you try to prevent or cure or improve a disease status, time is important, right? It's already difficult enough to make a treatment for humans, and you more count it in decades than years. But then there's only even that many shots you have in a lifetime, right? That one all of us have to be acutely aware of. And if we can do things to accelerate things, that would be really good. So what could we do to change things? We should do more robust experimental design. We should pre-register the experiments probably. That would be good, and publish less papers for that matter. We have to use good reagents. Good reagents are really expensive, and good engineering and good machines are even more expensive. That we have to be aware of that. We have to eliminate this positivity bias. Negative results should be readily available. If one of you has a great idea, you should have the privilege to go and look at the literature and say 5 times it worked, 5 times it didn't work. Let's see whether I can make a difference there. Sounds like it's not worked out yet. Maybe I can make it better. If you don't see the 5 times it didn't work, we're dead in the water from the beginning. Either you think it has already been done and it's an established concept, but often it is not an established concept. So it is an issue. I think the system is a bit in overdrive. We should publish fewer and better studies. It becomes really complicated, to be honest, because finding a solution for career evaluation in any of PhDs, MDs, in the biosciences, at the interfaces, it's not that easy. If we say, well, we change our view on papers and we don't count them as much. We have to have alternatives, right? And we have to be very clear. If we go back, for example, to writing letters and so forth, this is also a biased system. You might be in a lab, you don't get along with the mentor. Well, then you don't get a good letter. In my experience over the career, the people, which by nature happens because we have trained a lot of people, the people I didn't get along with for a variety of reasons, they all have excellent careers elsewhere. So that's an important realization, right? So that you look back at yourself and you go like, well, maybe it was me to a certain extent too, right? So it is like this. So we have to factor this in. We can't just say, oh, look at, you got 3 terrible letters. Well, that will be the end of your career. So we cannot go back to that either. So it's a fundamental problem, and it's not easy. And I'm not standing in front of you. I think I would have made the decision to have much more of a public voice if I would think I had all the solutions, but I don't. This is difficult, right? So it takes all of us to put our heads together to think about this, how this can be improved. Usually somewhere in the middle. And it's not all impact factors and papers for the careers, but it's also not just the letters and how you got along with a certain person and so forth. So it has to be somewhere in the middle. The pharma industry does this reasonably well, and they have a very thorough interview process, and they capture the personality, where you want to go with your life, how you create ideas or not, where you want to be in science. They capture all this, right? And it comes then, in a way, it comes then to a way where we also have to create more careers that not only driven by the principal investigator model, but you should be, because we all have different personalities. I like creative things, but I'm not very detail oriented. So I know this about myself. So if I want to create robust things in the lab, I need people who are very detail oriented. Otherwise, all the stuff I would touch is going to tank. You can count on that, right? So, and you can say, well, this balance has to be there. We need people who have ideas. We need people who are very, very good in implementing things and enjoy this. We need people who actually keep teams together and enhancing communication. And we need people who just drive visions. We had all these, can probably tell in pharma industry, you have all these personality tests, but it's not so bad. You understand better where you stand yourself, and you then understand better how everything relies on each other. And these career paths we have to create. We need more staff scientists. We need more roles and larger consortia where a position can derive stability and meaning. And these type of things, we have to adjust. We also probably need different funding models for that, because if you have staff scientists and you have these peaks and valleys from a grant, well, nobody in their right mind would spend the time and hire a highly skilled specialist, let's say, for a certain machine or area, and then what? The grant ends, specialists go home, you start it all over 3 years later. That cannot work like this. That would only happen if the machine or the whole area is a dead end, and then you would have to retrain, right? But you would have to create stable career paths. So somehow we need to adjust this, and the phenomenal challenge is we have to adjust it while it's operating and running, right? So that's sort of like fixing a car while it's driving. This is not easy. I mean, what, we're going to shut down all the universities for a year and remove things? That's for sure not going to be a good solution for anybody. So we have to come up with ways to rein this in the right way without breaking it while it's running, because of course there's also many good elements in the system. So I'm going to close on that. Sorry, now it's 1 o'clock, but we maybe have a little bit time of discussion. But I'm very open. You can always email me, because good ideas can always come. If we have good ideas, like this from Jay Schuyler to pre-register experiments, that's actually a really, really good idea. That would fix a lot of things, and then we could at least work on these type of things. Anyways, thank you for being here and for listening. Yes.
With respect to these financial hardships, how do you feel like that can be addressed, like at a university scale and at a research institution? Because we know the profound effects of diet and lifestyle on health, but you can't really make money by telling people to eat more people eat more fiber, even though it increases their solid blood pressure, right? So, I mean, UCSC doesn't even have like a nutrition program in undergrad as well. So how, it seems to me that what we need is more of a cultural shift, cultural understanding, into a paradigm shift, like washing your hands before surgery. Like, what is it going to take to push us there for cheaper and more effective solutions and interventions that are directly going to impact the most vulnerable who can't afford?
I mean, look, I don't hold the answers to that, while I think what you say is very true. We need a complete cultural shift in a system that went out of whack and went into overdrive, not because of people having the wrong intent, but just because it slipped out of our hands, and it was built at a different time for different purposes. And now we are 6, 7, 8 decades later in a system that needs to be adjusted. We need a cultural shift. We also, I mean, you alluded to nutrition and prevention. We need a cultural shift there too. Of course, I agree with you. I mean, metabolically, in terms of many things, nutrition is very important, and we need to have that cultural shift. It's a big area, the overall area of nutrition, because it affects what food we have available, where it is, how much it costs, and so forth. But yeah, these are big cultural shifts, and we have to gradually try to rein the system back in. In terms of the monies, that will have to come with it. We cannot have the expectation that we're going to do robust clinical or preclinical science if we underpower or have too little money in the experiments. There comes already a very clear, it's like building a house. You will tell me if I don't pour a foundation because I need to cut corner and then I leave out some beams at some point, you're going to tell me, you know what, buddy, maybe better put a tent on your lot. This is going to work better for you, but that house building will not go so well for you because if you cut that many quarters, it's not going to be solid. And we have to have this cultural change that we change that. It will be better for us. It will be better. It will be better for science. I'm really worried about this because during COVID, there was so many divisive discussions. And the divisive discussions could have probably been put at rest if whatever side people were on would have just taken a step back and said, well, this is not that solid. That's probably also not that solid. And this we really don't know. Maybe we have a conversation about that, what is really known. And then we can have a different conversation of what we maybe should do in a country to improve things for people during a pandemic. This somehow disappointingly got lost, right? That was very, very difficult, I feel, altogether. And it wasn't so good for the science. Things became very divisive, right? Yes.
One was scientific, so we need for a second. The first one was about, in terms of publishing itself, we know that, for example, journals, Eli now is shifting gears, and now they're starting to say that we're going to publish this study no matter what, whether editors say it should be published or whether reviewers say it should be published or reviewers said I would not publish it. So negative and positive comments get published together with the feedback. So that sounds like as long as you meet the criteria of this paper accepted for review, then your work will get published. So I was thinking in terms of how do we get negative results published? A couple ideas was one is maybe publish negative data together with some of the positive ones so that it gets wrapped into a package. And the second idea was maybe we could apply more for journals that have this, and maybe you can think of together.
I mean, I think these are great suggestions. I think I'm right now, I like this pre-registration idea, but I don't know whether we're ever going to come there. Because let's say if I try something and I'm thinking this is working great, and then you try it and it's not working at all, then the connotation in science has always been, well, you must be doing something wrong because it just worked beforehand. But the truth of the matter is, it might just be something on this curve here, right? That one time I did it and it is here, and then you did it and it's here. And it would take a very well-powered, well-organized study. And there's a legitimization for pilots. We should find out about pilots. Maybe you do something really cool tomorrow, but it's just a small study. It's very uncertain, but it was a great idea. So you get credit for the idea, but maybe it will fall apart a couple months later. That reality, that's where the cultural shift is. That's with that reality we have to live, and we can't penalize it in a way. And we certainly can't penalize when you look at it this way, that if it's one time like this and one time like that, that somebody did something wrong. What it means is, in a large sense, that the thing wasn't described well enough, so we can't control it. And then it's not like riding your bike, but it's much more complicated. It's really difficult, and you can't reproduce it, right? Sort of like if you play a really difficult violin piece and you think you have it on Sunday night, and then you play it on Monday and it sounds awful and you don't know an earth what you did different about it, but that means you don't have it yet for sure, right? But these ideas, they're great. We have to working towards, and I love publishing the comments with the paper because it takes a lot of political stuff out of it, right? Yeah, I'm still editor of Science Advances, and sometimes I just take reviews out because I go like, what happened here? You know, you couldn't even sometimes then publish the comment, and if I feel I can't publish the comment, even though the journal doesn't do it, I take the review entirely out. Well, I consider only if it has factual aspects. Otherwise, it's not possible. Right? You can't. Yes, please.
Going back to kind of the
Um, I think the public perception would profit from a narrative that is also a cultural change, where, at least to a certain extent, without complicating things too much, we have to accept that there is uncertainty to matters. That it's not as certain in biomedical sciences like building this building, and you can reasonably expect you're not going to fall down because every other day the thing falls over, right? We're not going to reach this type of certainty in some medical parts. Even if we mesh engineering and medical parts, there will always be that medical part that sometimes the islets live and then they don't live, and we have to really increase the robustness gradually. So the public perception is a little bit, it was in Time magazine that the scientific method represents the absolute truth. Of course, it's the striving for that, but it's always with a statistical uncertainty. We have to make that kind of clear to get away from these very divisive discussions, you know, that then end up splitting people rather than trying to understand what's really going on in a certain area. And funding is important. I think, as I mentioned before, building a house with the cheapest contract you could possibly get and cutting so many corners is going to get at some point in a really wobbly construct, right? But pilots are good. Pilots should exist as pilots. You know, we had a discussion at the DI the other day about a published paper, and the title read something that the diabetes was cured, and there was a press release, and we rewrote the title among ourselves and said maybe it should have been that, rather, that under certain circumstances there was some beta cells alive in the recipients and they still had function. And it's a good first step. That was not the argument. I mean, that was the reality when you looked at the data, but it was maybe a little bit, you know, over enthusiasm. I mean, there's a difference between stating what the data do. Then you can put your hope on it and say, well, this looks so cool. I'm so excited about my pilot. I really hope to cure the disease in the next few years. There's nothing wrong with that, but it has to be, you know. Yes.
the goal kind of have like 100 studies show that this works, 100 studies show that does not work. With that, where we start to take populations and say, okay, let's work for this people. Let's go on with that. So that'll stratify treatments one more specifically for this sports response. But when I talk to them, we don't science is a so again, how do you change that perspective around outcomes based on?
I think the way it's going to go, you need a big, clinically, and I believe in this concept, you design your trial and you want to meet an endpoint. If the trial is well powered and with that more robust in this figure here, you would be more ending up closer to where finally the reality is, okay? Then if the trial is big enough, you can do post hoc subset analysis and see whether there are certain patients who have driven this result from a certain region and certain genes, certain race. That would all be important, right? And that's where you're breaking things down into more personalized medicine that will start. You can say, oh, this diabetes treatment only seems to work for the young. This only seems to work for the older. This only works if you have a high BMI, and you're better off taking this drug. If you have a lower BMI, like for certain drugs for sure too, then you're not taking this drug. If you have a certain MHC, you respond well to a certain antigen. If you have a different MHC, you might not respond. So that, if you are well powered, this subgroup analysis you can conduct, and you can base your next trial on this and then validate it and say, okay, so this only seems to work in a certain HLA. So let's pick these patients and see whether we get a bigger effect size, even having lesser patients in the trial, right? So that's how it's going to progress. Ultimately, this vision that you might need a different treatment, that everybody gets their own treatment, that will come out of these subgroup insights. This will take us a long time to get there, but you take these factors into account, and then at least you can calculate certain likelihoods of responding to things. I think that's how it will evolve. You know, but at the premise is a blinded trial with a lot of power. This is important. And sometimes you can do more creative things. You could measure, if you have lots of historic controls, that might be useful to put a different light on your result, not only the placebo group, but what happens in that population in general. And you might have different historic controls in the sense of different races and different other factors you can include, and then see whether your results still hold up. They're doing this now in type 1 diabetes, where they're trying to predict. There was a very interesting paper from Carla Greenbaum, your individual trajectory. They take your age, BMI, and so forth, and say, well, this is your trajectory, and you got the treatment, and now you're here, looking pretty good for you. And my trajectory might be like this. So if the treatment does this, it would go like, well, probably hasn't done much, right? So it's getting there, but it takes a lot of power and a lot of data points to be certain about these things. But I think that will come. Hey, Claude, thank you for having me here. Thank you.
Thank you all so much for coming. There are leftovers,
Yes, indeed.
so let Dr. Von Herrath and Dr. Kravitz at the dessert first, but you get yours and you're good.
Okay. So
You
you
are?
can have it.
I'm just the lemon bar, then y'all can just send. So thank you again for coming. I appreciate it. Please don't.
Thank you very much for coming.
So I can-
Slide you showed you data
Thank
for
you all.
the combination therapy study.
Yes.
The patients who are on liraglutide alone did worse than.
Yeah, after the washout, that is, I didn't have time to get into it. After the washout, there was a lot of discussion about this, and that's why these things are not in the mainstream. We have to understand whether this worsening effect that actually interestingly did not occur in the combo group. Right. So there's two theories. One is liraglutide burns the beta cell. One possibility. For my boss at Novo Pulse was flogging the beta cells, and then they're gone. What argues against this? They didn't burn out while they were on the drug. Right? If you make me run a marathon, I can tell you I will burn out before reaching the finishing line, and not conveniently right after I've reached the finishing line. So that's a